And today we are going to continue our talk about this review of material science. And last time we stopped at the phase. When we talk about the phase, we stopped. Today we are going to continue our talk on phase equilibrium. So this is a free phase equilibrium. We know equilibrium, right? We have learned mechanical engineering for several core courses with me. For example, computer-aided engineering, machine design, and also this machine design. And we have learned this state of equilibrium. Phase equilibria is a plural form. And so it means that it is in a state of equilibrium also. And here we are going to talk about several important concepts on free energy. Free energy is a function of internal energy of a system and also the randomness or disorder of the atoms or molecules. And so the second one is equilibrium. A system is at equilibrium, is a free energy, is at the minimum level, and some specified combination of temperature, pressure, and composition. And we should know that in the universe, in the nature, every system tends to reach the minimum level of energy to remain stable. So this is the principle of all these the systems in the universe. And then we talk about phase equilibrium. And phase equilibrium refers to equilibrium as it applies to systems in which more than one phase may exist. It is reflected by a constancy with time in the phase characteristics of a system. Another one is a metastable state. It is often the case that a state of equilibrium is never completely achieved, because the rate of approach to equilibrium is extremely slow. So this is a metastable state. And such a system is said to be in a non-equilibrium or metastable state. A metastable state or microstrata may persist indefinitely is long time, so experiencing only extremely slight and almost imperceptible changes as time progresses. So read this statement: a metastable state or microstrata may persist indefinitely. Indefinitely is a very, very important word. Experiencing only extremely slight and almost imperceptible changes as time progresses. And we then talk about phase diagrams. Phase diagrams indicate phases as a function of temperature Tc, T temperature, C composition, and P is the pressure. So for this course, for material science, and we have several different systems, binary systems. Binary system, as the name suggests, binary means we only have two components. So independent variables, and we focus on temperature and composition. And regarding the atmosphere, and regarding the pressure, we just assume atmosphere pressure, and it's almost always used. So for this case, we only focus on two components and focusing on two important variables, temperature and composition. So this is a phase diagram of copper and nickel system. So this is the abscissor is a weight, and so here is this ordinate is a temperature, and we can see liquid and liquidus, and liquidus is a curve, and whenever so where this is a liquid and transforms into the solid, the solution, the combination of solid, and this is a liquid. And solidus means we only have this the solid material. So we have two phases. One is liquid phase, one is this olive phase. Olive phase is FCC solid solution. So we have three different phase fields. One is L, the pure liquid. Second one is combination of liquid and solid, and the third one is purely the solid. So we have three different phase fields. So isomorphous binary phase diagram. So there is a special binary phase diagram called isomorphous. Isomorphous, as the name suggests, iso, whenever we see iso in English language, we know that something is the same, okay? And something is the same. And here, so isomorphous, the binary phase diagram is to talk about these two components, copper and nickel, and they have a lot of um, they have they have many they are in common. They have many things. They share many the characteristics. So this is copper. You can see from 1 to 100% of nickel, and here this is 100%. This is 100% nickel. This 100% is copper. And so this shows that these two guys, they can solve each other completely. Okay. The system is binary, and so these are two components, copper and nickel. Second one, isomorphous. As I said, iso means something is the same. So here, complete solubility and complete solubility of one component in another, one component from copper to nickel. The alpha phase field extends. So this phase field, this alpha field extends from 0% to 100% with percent of nickel. So this is called isomorphous. So in order to have isomorphous binary this binary phase diagram, so there are some criteria and needs to be met for solid solubility. Okay, so simple system, for example, nickel and copper solutions, nickel and copper breakdown, and then you can see crystal structure, FCC, then electron negativity 1.9, 1.8. These two guys must be very, very similar. Otherwise, they cannot have isomorphous this binary system. So radius and these two radii are very, very close also. So both have the same crystal structure and have similar electronegativities and atomic radii. So this is called Rossary rules, suggesting high mutual solubility. So nickel and copper are totally soluble in one another for all proportions. So phase diagram determination of the phase present. And rule 1, okay, if we know temperature and composition, and then we know on which phase are present. If we know temperature and we know composition, and we know where this point is, then we can look at whether this is liquid or this is a solid or the combination of liquid or solid. This is for example. At point A, this one, this temperature and also the 60 weight percent of nickel, and we know this is alpha. Point B, and 1250 degrees C, 35 weight percent, and we know this guy is in, and this is liquid plus solid, this phase. And rule 2, if we know temperature and the copper decomposition, then we can determine the composition of each phase, right? Composition of each phase. And consider ZC0 at temperature A. Only liquid present is based on rule 1, and we know Cl equals C0 equals 35 weight percent. At temperature D, same composition, only solid alpha, and C0 equals C alpha equals C0, still 35 weight percent. And at point B, which is located in the combination of solid and liquid, the phase, and both alpha and L, and they are present. And then we draw a level, we draw a horizontal line, and so this line intersects the liquidus curve and solidus curve at these two given points respectively. And then we draw horizontally based from this interception point and this intercepting point. And we know that here CL equals this point. And C alpha equals this, right? So you can get the composition of these two faces based on this rule 2. And rule 3. And if we know T and C0, then we can determine the weight fraction of each face. That is amazing. So for example, still use this example. We draw the horizontal line here, CL, C alpha, right? So at TA, we only know liquid 100%, alpha is 0%, D solid 100%, liquid 0. At point B, we draw a horizontal line here, and both alpha and L present, and you can see WL with liquid weight equals, for these two equations, the denominator equals each other, they are the same denominators, but the numerator, and pay attention to the numerator, okay? So for liquid, we use another arm, and for this solid, we use this arm. And so this one, you need to be very, very careful, otherwise, and your answers will be wrong. So this is the 3 rules. And the level rule, so this is called the level rule, right? So the level rule, the line connects the faces in equilibrium with each other, and also sometimes called isotherm. Therm means temperature, right? So what fraction of each phase? Think of the tie line as a lever, theta total. So this is theta total. This R and S. You can see we know that. So this is balance MA multiplied by S equals ML multiplied by R. So we can get this is WL, okay, equals ML plus M alpha equals this one equals this. And similarly, we can get this alpha. Any questions regarding this slide? And then we talk about binary eutectic system. So this is the Ag, the silver, and so this is the temperature, and this is the composition of copper and silver, and so this one is binary, still binary, 2 components. So binary eutectic system. So this is copper and silver. The 2 components has a special composition with a minimum melting temperature. So here is a eutectic point. So 3 single phases, and we have alpha, L, alpha plus beta, limited solubility, and so you can see alpha mostly Au here, mostly Au copper, beta mostly silver, Te, so this is a eutectic system, and Te no liquid below Te. You can see no liquid below Te. This is Te. So Ce composition at the temperature Te. At this point, you can see if we have the phase transformation from liquid to solid, we can have 1 liquid phase, then we have 2 solid phases, alpha plus beta. So be very, very careful. This is called eutectic system. This is eutectic phase transformation. So then we talk about the example, the PBSN eutectic system. And can somebody tell me for this diagram, where is the eutectic temperature and where is the eutectic composition? Why? So here, okay, so this point is answer alpha plus beta, okay, the phase composition. So here, this is answers, and we can still use the level rule to calculate the weight fraction of two different phases. Example B, the phase present for 40% with percent at 220 degrees C. Here, this is alpha plus L. The phase composition, and draw a line. Okay, draw a line here. So from here to here. So C alpha 70% and C this Cl liquid is 46%. The relative amount of each weight, this weight fraction, and we use the lever rule to calculate and draw a line. Okay, SR. Be careful, SR. So microstructure development in eutectic system. So for alloys for which the composition is less than 2% of Sn result at room temperature. Here, polycrystalline with grain of alpha phase having composition of C0. So polycrystalline with alpha grain. You can see. So you can see this we have alpha here. This is solid. So this one is polycrystalline. This is polycrystalline. This the grains, polygrains. For another range, from 2% to 18.3%, and we go here 1, 2, 3, 4. We have 4 fields. Then we will experience. We will go through 4 fields. At room temperature, alpha plus beta range, alpha plus beta range, alpha plus beta range. Polycrystalline, this liquid, alpha plus L plus alpha. So this is the alpha. Okay, you can see this alpha solid. So this is alpha. Within this alpha, we have these beta particles. For another range, for this part, eutectic microstructure, lamellar structure. Okay, so lamellar structure, lamellar, you can see lamellar. What is lamellar? Alternating layers, lamellae of alpha and beta phases. You can see this one. So you can see lamella. Okay, lamella means alternating layers of two different phases. Very, very beautiful. You can still use our lever rule to calculate the weight fraction. And this is a micro graph of this system. It's very, very beautiful. This eutectic for another range. So this is the L plus alpha. So it is still alpha L plus alpha. Can still use the lever rule. And so here is a primary alpha, eutectic alpha, and this is eutectic beta. Okay, eutectic alpha and eutectic beta, and they form the lamella. And the primary alpha is alpha we got here, and it was just like balls here. It's very, very beautiful. Then computation for relative amounts of primary and eutectic microstructure, and we draw a line here. Okay, P, Q, and R. So these equations, I want you guys to take a close look at these equations. So we have eutectic, eutectoid, and peritectic, the phase transformation. Eutectic and liquid and becomes two different solid phases. Eutectoid, one solid phase transforms to two other solid phases, eutectoid. Peritectic, as the name suggests, peri, okay? Peri is kind of half liquid and one solid phase to a second solid phase. So this is the be very, very careful about this. So congruent phase transformation, and phase transformation for which there are no composition alterations. For example, allotropic transformation. This is from alpha and beta. These alpha and beta, they are from the same material. Okay, incongruent transformation, and at least one of the phases will experience a change in composition. And for example, eutectic and eutectoid, as well as a melting of alloy that belongs to a isomorphous system. So this is a congruent phase transformation. And then we talk about iron carbide phase transformation. As I told you guys, and when we learned this topic, so this is the most important. Iron carbide is most important still, and the most important phase diagram. So here, this is very, very important. And first, iron carbon, we call iron carbon or iron carbide phase diagram. And two important points. Eutectic, A, eutectic, from liquid to two solids. And eutectoid B, here, from alpha to two, from the alpha solid to two different other solids. This is eutectoid. Very, very beautiful. This is a lamella, cementite, hard, cementite, FeC3. So this is a micrograph. So cementite forms when the solubility limit of carbon in alpha ferrite is exceeded below 7 to 7 degrees C. So this is the 7 to 7 degrees C. The cementite also coexists with the gamma phase between 727 and 1147 degrees C. Mechanically, cementite is very hard and brittle. The strength of some steels is greatly enhanced by its presence. So this eutectic and eutectoid reaction. Eutectic and eutectoid, we talk about this one, and I want you guys to look at this one by yourself. Development of microstructure, and so here, okay, so you can see hyper-eutectoid. Hyper means the composition is lower than the eutectoid composition. So here, this eutectoid composition, so here is a hyper-eutectoid steel, this gamma austenite. And then we have, this is this is the dots there. And so this is dots, alpha dots grow. And then we have pearlite. Okay, this is a pearlite, means this is the lamella, this is a pearlite. So this is a pearlite. This is the dark area, this is alpha. This is a pro-eutectoid ferrite. And hyper-eutectoid means the composition of carbon is higher than the eutectoid composition, which is this value. You can see, so this gamma, and then we have, this is cementite, Fe3C. Going down, we also have pearlite, this lamella of pearlite, so this is a micrograph. So then we can use the level rule to calculate the relative, the weight fraction. So we still use this value, this equation. And so I want you guys to take a closer look at these equations. Then bainite, another another iron carbide transformation product. So bainite, elongated cementite particles in alpha ferrite matrix, diffusion controlled, isothermal transformation diagram, isothermal, temperature does not change. This is for this C0, 0.1776 with percent. Austenite stable. Okay, so here, so we go down and then hold the temperature. So here is 100% of pearlite. So this is the fine pearlite. Okay. So if we go down, we have the bainite. This is bainite. And then we have another one, spheroidite. Spheroidite means something look like a sphere, right? As the name suggests, and another microstructure for iron carbide system, spheroidite. You can see. So these cemented particles within oligoferrite matrix, so we call this coordination. We can call this coordination because two different phases. Formation requires diffusion, diffusion of either carbon or this ferrite, this iron. Heat bainite or perlite at a temperature just below eutectoid for a long time. And then the driving force is reduction of oligoferrite and this cementite interfacial area. Why? Because the reduction of this interfacial area can reach a minimum level of energy for the system. As I said, I told you many times, so all the systems, they tend to reach the minimum level of energy in order to be stable. Then we'll talk martensite. Martensite is very, very important. A non-equilibrium transformation product. Right? So you can see like needles. Martensite from FCC to martensite BCT. So this is a BCT. The crystal structure changes. So as a thermal transformation diagram, and when can we get this martensite, and when the system, when we have very, very high cooling rate. And for here, this cooling rate does not intersect with these two curves. And then we can get this martensite. Martensite, very rapid, diffusionless, and because the time is very short. And the percentage of transfer depends on the temperature to which rapidly cooled, the final temperature you want to achieve. So martensite formation, FCC slow cooling, and we will get alpha and the cementite. However, quenching, we can get martensite, BCT, as is another crystal structure. So martensite is a single phase and has body-centered tetragonal BCT crystal structure. Tetragonal, diffusionless because the short time. So as a result, BCT has few slip planes, and also it's hard and brittle. And this is usually the martensite material, martensitic material cannot be used because it's too hard. And then we need to temp it in order to get a better tempered martensite, which is more ductile than the original martensite, but still very, very hard. So this tempered martensite BCT to tempered martensite alpha plus cementite phases. So this is a summary of microstructures and the properties for these iron carbide diagrams. And be very, very careful, as I said. So this diagram is the most important diagrams I want to emphasize for my students. And then we talk about this classification of metal alloys. For metals, we have metal alloys, ferrous, non-ferrous, right? For ferrous, we have steels and cast iron. And what's the demarcation line for steels and cast iron? So that is the composition of the carbon. And so these steels, we have low alloy or high alloy. And for low alloy, we have low carbon, medium carbon, and high carbon. For cast irons, we have 5: green iron, ductile iron, white iron, malleable iron, along with compacted graphite iron. So I'm going to stop here now, and we will continue talk in our next class. Thank you very much.